now on one screen but not the other, which means it's a hardware problem. Okay, guys, why don't you all go over? Okay, oh, momentary success. Let us get the talk done while we are in. Okay. Okay, is it okay if I remove my mask here? So it's, if people are far away from me, it's fine. Okay. Okay, so I'm going to talk about, this talk is really two sub-talks. One talk which is about robotics, okay, and
not anything you do.
yeah. Okay, fine. Wait. Maybe can people see that from there? Okay, fine. Patience. Okay. So this talk is two talks. One part is about robotics and the other part is about video understanding. So, okay, so it was supposed to be about masked visual pre-training, but you can see that the slide itself is masked now. Okay. 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 So this is the problem that we are trying to solve. So, okay, I'm gonna, I think I can even give this talk without slides. I'm gonna just give the high level. I'll give the high level view. Okay. Let's see how far I can go. So the problem we're trying to solve is robotics, and in robotics we want to use deep learning. So if you know, it's well recognized that deep learning has had its earliest impact was in speech, then in vision, and then in language. And these three areas have been totally changed over the last so many years, and the use of big data has helped. Interestingly, there has not been that same kind of impact in robotics. And there are reasons for this, okay? Because robotics is an active problem, so you need to, what you see changes based on what actions you perform. So you sort of need simulation environments if you want to have a very large number of trials. And then with simulation environments, we have the challenge of the sim to real gap. So you can work completely in simulation, which works for some things, but then when you use real world images, you get a problem. So these are kind of the reasons, I'm oversimplifying, why robotics has not had that same complete takeover of deep learning as has happened in the case of the other problems that we are interested in. So these are examples of the problems that I'm interested in. So this is picking up an object, opening a drawer. Okay, more examples. And what do we want here? We want generalization, right? So you want that there could be different objects on the table, there could be different locations on the table, and it should just work. That's our goal. Okay, it could be a banana, and so on. Okay, so what do we need? There are two kinds of generalization we can talk about. There is generalization in the space of perception, and there's generalization in the space of action, right? So the big idea, actually it goes back to RCNN, is that we pre-trained an image set, and then we had a representation which could then be fine-tuned for other data sets where you didn't have much data available, right? So there was a generalization and transfer. In that case, we're talking about for recognition tasks. When we talk about some motor action, like picking up objects, we can talk about generalization on the sensory side or generalization on the action side. So generalization on the action side would mean that if you have learned 20 actions, learning the 21st action becomes much easier. Generalization on the sensory side means that if you know about 20 objects and you can recognize them, recognizing the 21st object becomes a bit easier. Both problems are interesting. I'm going to talk about the first problem, generalization on the sensory side, on the perception side. Okay. So the idea here is that we are going to use a pre-trained encoder on the vision side. And this pre-trained encoder can make use of huge amounts of training data, essentially, millions of images, let's say. And with that pre-training, it becomes, there is a visual representation, which then enables us to generalize on the sensory side. On the action side, we'll keep it vanilla. It's going to be trained for particular tasks, and that's all we'll do. Now, what's a good representation for generalizing on the sensory side? Okay, so there is supervised techniques, right? You can train a supervised network based on ImageNet or whatever else. And CLIP is another example. It's weakly supervised with language, but it's still a supervised setup. It's the other line of work which has been going on now for like 5-7 years is self-supervision without labels. Okay. And in that line of work, there is a very recent paper from FAIR, led by Kaiming et al., called Masked Autoencoders. It almost seems like it's in the past, but actually it's in the present. The paper will be presented at this CVPR. And the idea is quite simple. The idea is that we are, I'll tell you the idea in a second, but we're going to use that as an encoder for the visual knowledge. Okay, and it's going to essentially enable transfer based on huge data, big data. And the other input that you need into the system is proprioception. So what do I mean by proprioception? Proprioception means knowledge of your own body. So in this case, it means joint angles for your hand and wrist and arm and all that stuff, right? So so when you're performing an action, you know the state of your own body, you have the visual input, the two together are used to determine your actions. Okay, how are we going to train this visual encoder? So this is where the big data comes in. So the big data is that you need lots and lots of images to train this network. Okay, but we don't need labels, we don't need language. Okay, the kinds of images that will turn out to be the most helpful are ones which correspond to manipulation of objects in the egocentric view. So, there are a number of egocentric data sets out there. There is a new, very big one that we created recently called Ego 4D. And it turns out that that's like the game changer. It's like the revolution that was caused by ImageNet, 10 years ago. That's the revolution that we are going to get for egocentric data because of the availability of Ego 4D. Okay, it has 3,500 hours of video recorded by 1,000 different participants. And these are examples of egocentric video. Okay, now what is the self-supervised learning technique? Okay, this is a paper which is at the CVPR called Masked Autoencoders as Scalable Visual Learners from Kaiming, Ross, Kershik, and others. So check that paper out. But the idea is super simple and it connects to transformers. You're probably wondering why I'm busy talking about all this stuff and this is a transformers workshop. Well, this fits into the transformer framework. So the idea is you take an image, you patchify it. So here you see like 25 patches. And what you do is you get rid of lots of those patches. You mask them. And then the remaining patches are available and they are transferred to your transformer encoder. And then the job of the transformer encoder is to predict all the remaining patches. So basically, you see the image on the left, the masked image, the network has to see that and it has to reconstitute the image on the right. Okay, and amazingly, it can do it. Okay, I'll show you some pictures. So look at how much of the image has been masked away and yet it can be reconstructed. And reconstruction is simple, just L2 loss. Now, a system which is capable of doing that has actually got a lot of knowledge of the visual world. Because, for example, for this Rubik's Cube, think about going from the masked image to the target. So it pretty much sort of has to know where the object begins and where it ends. So it kind of has to know the boundary of the object, the mask of the object. Now, why is that important? If I'm going to do grasping, I need to pick up that object. So I need to know the boundaries of the object. So this is where I think there is an advantage over the use of language. So if there was language supervision which says this is a Rubik's Cube, that's good. You would put a label. But that won't tell me the boundaries of the object and the shape of the object, because that is what I need for doing a robotics task. So I think we are overfitting on language right now because we have all this great technology for language. But if we want to do robotics, we have to, words are not so important. Space is important, time is important, forces are important, things like that, right? Okay, now these are pictures which are just showing the power of this MAE, masked autoencoder model. Okay, Microsoft PowerPoint has stopped working. Okay, can we cancel this?
Yes, yes, it happens. It should be fine.
Okay.
Need a while because it's
Okay.
going to restart.
Thank you. Let's see. Let's do this. Okay, so we're back to where we were. Okay, so so you look at the image on the left, right? Each of these has 3 panels, right? The image on the left is what's the masked version. The one in the middle is ground truth, and the one on the right is reconstruction. So I find this like shocking, right? This is amazing. How little the information is there after masking, and yet the image can be reconstructed. So the representations that are built up by this system, which is able to do this reconstruction, have to be pretty damn good. And what we're going to do is use those representations frozen. So we'll compute these representations, and this is now this is like your visual expert. So the vision expert is this masked autoencoder, which can, given any image, has this capability. And we are going to now use it for robotics tasks, and then we are going to give it real images, but it's been pre-trained. Okay, and these are the kinds of motor control tasks that we'll do. So picking up objects, reaching objects, pushing objects, opening drawers, and so forth. And then like all such talks, right? They have to have some results slide, and I have to say my results are better than your results. So this is that kind of a slide. But the point here is that we now can compare different visual representations. So the representation built up with MAE versus a representation built up with, say, supervised labels on ImageNet or whatever else. And the test is that from this visual representation, we are going to train for a robotics task. And that robotics task can be trained with either reinforcement learning or imitation learning. And we want to learn the task quickly. So one test is how many trials does it take to get a certain performance? And another test is generalization. Does it generalize over different objects? So sample complexity should be low and generalization should be high. And now we can compare different visual representations. So we can compare a visual representation which is ImageNet with supervised. You can compare an image representation which is a clip, which is weakly supervised with language. Or you can have a representation which is masked autoencoder on a bunch of images, but these are images of from egocentric video. Okay. And and all these curves, if you deciphered them, they all say that basically. So it outperforms the state of the art on image-based reinforcement learning. Okay, so look, here's one I'll point out, because there's a blue curve and the yellow curve. And CLIP is like the biggest models we have currently for vision and language. It's like, it has like 400 million images. Okay, and look at our curve. Okay, the blue curve. And the point of it is that in far fewer steps, it's able to get to a higher level of success, which means that it is a better representation for robotics tasks. I'm not trying to convince you that this is a better representation for everything. I'm saying that there is in our brain, in fact, this is true in the humans, we start off with information in the visual cortex, and then there are these two streams, one which is called the dorsal stream, which goes in the back, and one which is called the ventral stream. So the ventral stream leads to recognition and connects to language and cognition and so on. There is the dorsal stream, which connects to action, okay, motor cortex, etc. We have been spending most of our time in this community writing 90% of our papers are on the ventral stream, object recognition and connecting to language. Whereas in fact, when you were a primate, your survival depended not on language, but being able to find fruit and eat it, otherwise you would starve. Okay, so action is really more important than language, right? So, and the visual control of action. So what we are trying to do here is to say that you need the right kinds of representations for that. And we are giving you an example, which is train on lots and lots of egocentric data with a masked autoencoder, create that as a visual representation, and on top of that, train for robotic tasks. And these were results in simulation, so one should always be wary, but let me take the lessons here. Single visual encoder pre-trained on real-world images can solve various motor control tasks. Self-supervised does better than supervised. This is great, right? Because for years we've been fighting the battle of self-supervised results are like within 1-2% of behind supervised approaches. And then pre-training on images in the wild from YouTube or egocentric videos works better than ImageNet. And the latest results are we took these ideas and applied them on real robots. And this is a paper with the following authors. And it works basically. So this is to convince you that there's a real robot and real objects which have to be reached. And these what's a generalization that we want? The object could be at different locations, it could be a different shape, and it should still be able to pick it up, right? And that, so let's see if it does. Well, because I have this in my talk, it must work, right? Okay. And then here it's opening a fridge door. Okay, it's picking up some fruit, some other object, and note the complexity of the scene. So there is the object of interest, and there's a whole lot of other stuff, and it still picks it up correctly. So it needs to know about objects, object boundaries, and objects in scenes, which is the kind of knowledge you get from just looking at images and understanding the structure of images. It does not, this system does not know that whether it's looking at a pear or an apple. It can't name it for you, but it can pick it up for you. There's a difference between naming and picking. And this is about picking or pushing or grasping. Okay, same general approach, real world data, mass pre-training, and then a whole bunch of robotics tasks. And how this was trained is interesting. There are two basic methodologies for learning on the robotics side. One is reinforcement learning. It's very expensive and it needs a good, because it needs a simulator. You can't do it in the real world because you won't make enough trials. So if you have a good simulation environment and you're willing to do 1 billion trials, it will work. And we have work on walking where we did it that way. For manipulation tasks, if you have to do it on a real robot, reinforcement learning is not so practical. But demonstration learning is, so which is that you learn from observing others. And that's what you are going to see here. So Ilya is going to use sort of remotely control this hand, and he's going to manage to get it to pick up this object or touch it in this case. And then he'll just repeat, he'll do these experiments. So he does like 80 experiments with these objects in different positions. And with that, then it becomes a supervised learning problem, because you have all these examples of what action to do for these 80 trials. That's known. And what you do is that you hope that your network generalizes. Okay. And this is, by the way, a movie. So the camera is mounted on the hand. So what's happening is visual servoing. So the hand moves, and as it is, it keeps the object in the center, and basically the object is becoming big because your hand is getting closer to the object. So roughly speaking, that's the signal which is being captured. But you trained in some setup, and then let's see whether it works on all these other objects which were not part of training. And I mean, you're just seeing the camera view, but actually it does manage to pick up. And now we add clutter, we make it a complex scene, and it still works. Okay, so the basic setup is there's a image encoder which is frozen, which is pre-trained using 100 million images or whatever, and then it's the policy is what is trained, and these are just more examples. Okay, so performance. So now it's a real world task, and there's a performance of our system. Then clip something. So these encoders can be trained with this way with master autoencoders, or they could be trained with clip, or say supervised on ImageNet, or you can start to learn from scratch. And you see that the best performance is on the left, which is with this master autoencoder with just images with no supervision, no labels. And then on various tasks like reaching a block, pushing a cube, picking a cube. And it reaches the clip performance with like 2 times fewer demos. So one case you might need 80 trials, here you need 40 trials. And then generalization to tasks like this. So notice that this fridge door, it could be on the left, it could be on the right, there's some other junk, it works. And then the video is doing some strange stuff. Okay, what's happening here? It's got stuck. I want to go to the next slide, basically. We can go to the next slide. We are done here. Okay. Yeah, that's fine. Okay. And now this. Yeah. Okay. Thank you. And then the more visually complex the task is interesting. More visually complex the task is, the gap with clip becomes more significant. And then what we are also seeing is the thing which we want with big data, that you get a power from more data and from more bigger models. So models with more parameters do a better job, but they also need more data. And that more data is available with this Ego 4D, which has like 5 million images. So that's a video stream, so we sample it with like 0.2 frames per second and use that. So this is great because we always want to get onto the train of big data, where after that you just make it bigger and it gets better. And people have done this for vision and language. Here we are showing it for vision and action, but actually on the vision side of it, there is a similar story to be built up on the action side. And I've already gone on too long because we have all the other things. So let me just spend 5 minutes on the second half of my talk. which was going to be on multi-scale vision transformers. And this is a group at Meta, and here are the names of the authors: Hao Chi, Fan, Bo Xiong, Karthik Mangalam, Yang Hao Li, Jisheng Yang, myself, and Christoph Eichenhofer. And we presented this paper at ICCV 2021. And the code is available as part of PyTorch video. And let me give you a little bit of the big picture. So the big picture is how do we transformers for video? Okay, transformers for video. If you want to have lots of patches, and so okay, for now, let's just go through and not worry about it. Okay, the basic challenge is complexity, right? Because it scales quadratically, and if we are going to have not just one frame but many frames, we're going to get into trouble. So one idea for this is like the swing transformer. That's one of the popular techniques out there. So this is an alternative technique which I think works better, which is to combine the idea of transformers with the old idea of multi-scale. Okay, so the idea of multi-scale and hierarchy is, I can talk without, okay. Multi-scale and hierarchy is a very old idea in computer vision. It goes back to Hubel and Wiesel, who had these findings on receptive fields in monkeys and so forth, somewhere around 1960. And this was responsible for the design of the neocognitron, which when backpropagation was added became convolutional nets. And in computer vision, we have had other ideas like pyramids, Gaussian pyramid, Laplacian pyramid, and so on. And the basic, what's a big picture idea? The big picture idea is that at the lowest levels of a neural network, you have lots and high resolution, lots and lots of pixels. But the channel dimension is very low. Channel dimension is just RGB, like 3 colors. So the channel dimension is 3. As you go higher up in the layers of the convolutional net, what's happening? You are decreasing your spatial resolution, right? And you're increasing your channel dimension. So the channels become very complex. They are encoding for faces, apples, bananas, zebras, and so on. But they are finding the object independent of position, which could be anywhere in the image, because the spatial resolution is being lost. And this is the idea behind all the ConNets like that we have been using in the field. And now we move to transformers, and transformers have all these patches, but then it's the architecture doesn't after that do anything for you, right? So the transformer keeps the channel dimension, right? The embedding vector is the same size at all the levels. And our basic conjecture was that let's try to combine this with our old ideas of, as you go higher up, reduce the spatial dimension, expand the channel dimension. So just working out the details of that is basically the multi-scale vision transformer, which I hope you would see the picture, but okay, you're seeing it. Now you see it, now you don't. Okay. So you start out with lots of patches at one scale. And then as you go to higher scales, these are, oh my God, okay. Okay, so basically you're going to get fewer entities, and then as you go to the next stage, it's going to get fewer entities, and it's going to go through various transformer blocks. Okay, I think that's all that probably is worth explaining at this time. Okay, channel dimension will go up, the number of these patches will decrease, but each one will be bigger embedding vector. And how we do this, there are a couple of, now we get into the technical details of, there is the query, the key, the value, and you can pool and queue, or you can pool and KV. And I think it's late and you want to have lunch, and I'm going to skip all that. Okay. So read the paper. It was published at the last ICCV. And then, so we'll have a design with all the details. So I'm skipping all of that. and then you can explore attention maps. Anyway, the marketing side here is that this works, and we can have this model in different resolutions, and it gives a good trade-off in terms of flops and accuracy. And okay, so this, I'm not going to go into all the details here, but I mean, read the paper. The paper will basically say our work is the best. Every paper says the same thing. Okay. Okay. But it really is very good. Okay. And that idea applies for video or for images, because we can simply just run it in just a spatial dimension. And what we have is, okay, so here the takeaway, it expands feature complexity while reducing visual resolution, shows advantage over single scale visual transformers. It's not surprising, it's just a classical computer vision idea. See, we took the transformer idea from the language people, okay? And we just said, okay, let's just do it, and it works for us too. But let's not forget our classic computer vision ideas of course to find. Once you have that idea, you combine it, that's what MVIT is. And it really is good, it works. Okay. And then, so there is, MVIT was at the last conference, and this conference we have 3 papers. There's one called MVIT, MEMVIT, and there's an idea of reversible vision transformers, and then there's MVIT V2. And please check those papers out. I think I have slides for these 2. So this one actually shows the photos of the people, but go to the papers and have lunch now. Thank you. I apologize for all the inconvenience and your patience. Thank you for your patience.
Yeah, truly sorry for all the technical issues. And I mean, if you, Jitendra, do you have a few minutes for questions?
I'll answer questions. Yeah. If you have questions, I'll answer them. Yeah, of course.
Thanks a lot for a great talk, Professor. No disrespect for anybody. Your work is very great, and mask autoencoder were very great as well. We demonstrated that in April 2021. And in parallel to that, when you are saying that we know where it is, with all the benefit and all the complexity you are showing of contextual information and localization, on top of that, in parallel to the work from Facebook AI Research, we also started to associate pseudo label to it. So we can not only localize all the object using GMML, we didn't call it mass autoencoder, it's the exact similar thing, but we call it group mass model learning. But on top of that, we started to assign pseudo label to it. So now you will not know that this is Apple, but you will know this is concept 1 or concept 100 or concept 20. So maybe it will be very interesting. So I would like to pick up your thoughts. The poster is also presenting here.
Okay, good. Thanks. Good to know. Yeah, thank you.
We have maybe one virtual question. So in the robotic applications, do you have any insights sort of what the model is learning to attend? Like what's a intuitively visual representation that's allowing it to perform actions?
I think that so the representation was built up for doing this completion task, right? Now to do the completion task, it must know about objects. So we didn't teach it about objects. So the world contains objects. I think that knowledge is very important for robotics. And in order to do this completion task, it had to know about object boundaries. So therefore, and that knowledge I think is what is most important for deciding on how to pick up objects. Now, there might be other ways of getting that in. For example, there might be a segmentation system or whatever. But we have to train it without labels, which is a challenge because typically instance segmentation systems are trained with boundaries and masks and so on. So I'm not saying that, so I think that this is, over time, this will emerge as to what's the best visual encoder. But what I want to try to encourage people in this room is robotics is important. And I think vision people can contribute a lot to it because in fact, so far, the reason why robotics is not advanced as much is because they have not devoted enough time to the perception part of the problem, which may be more than half the problem. Anyway.
Maybe another question, Zarastova. I've been working in robotics learning, and there are two schools in vision-based robotics learning. One is that we need to segment all the objects in the scene so that the robotic manipulation can be easily performed. And another school is we can just fit the model with a general visual representation of the scene. We don't need to have a segmentation task and so on. How do you think about the way to proceed?
Yeah, so the work that I presented did not have explicit segmentation, right? The segmentation is implicit in that representation, okay? So this one, we did not do explicit segmentation. Now, I think time will tell how it works. So currently what's happening is that, I mean, I have worked a lot on segmentation myself. Okay, I love segmentation, I love grouping. I feel that what we need are general purpose category agnostic segmenters. So a segmenter like mask RCNN is category specific. Whereas in the previous generation, we were developing category agnostic segmenters. I think we need category agnostic segmenters. Secondly, the right segmentation depends on the task. If I'm picking up a bunch of jelly beans, sometimes one jelly bean is the group, sometimes the entire set is a group. And therefore, the segmentation needs to be hierarchical and soft. So there need to be certain advances in the space of segmentation before the segmentations are perfectly aligned. The classical roboticist used a very simple-minded notion of segmentation. And I think that compared to that, these representations are better. But I feel that the final word is not out yet there.
People say that it depends upon the affordance.
But affordance is the action part, which is related to the shape and positioning of the object.
Yeah, the
So
future
that
use.
could be in either setting.
Okay, thanks very much.
Hi.
Yeah.
Do you have any opinions on how humans and animals learn very quickly to act? Like for example.
Well, it's actually not clear that we learn very quickly to act. When there's a child and they're learning to walk, they fall a lot. There's a paper from Karen Adolph that they have hundreds of falls and so on. Okay, what happens is that's why do children go to school at the age of 5? Okay, they go to school at the age of 5 because that's the only age they're able to manipulate a pencil, which means that they have taken many years to develop the fine motor skills. Now, what we have is very good transfer later on in life, right? Because you've forgotten all this stuff because that happened when you were 3 years old. But you went through a lot of trial and error when you were young. I mean, like even the vision, this is true for vision and it's true. So there was a lot of data and a lot of trial and error when you were 2 years old, 3 years old and so forth.
But some like newborn calves can.
But they don't have flexibility. I think the thing is that humans have chosen to have late development and more flexibility, whereas there can be animals which have not much flexibility and then they're ready, then it's pre-programmed. So there's a choice in evolution that a species can make, and our species has made the choice of late development, but a lot more learning so we are more towards nurture than nature.
Got it. Okay. I have one more question, which is in terms of vision for supervision for vision. Do you anticipate 3D and motion and flow to be more useful than these kinds of token predictions?
No. So here the information about motion is coming in because you have many frames. So the action is being performed through many sequences of images. There's an image sequence coming in and there's an action sequence coming out. So the motion information is there. Depth is implicit because as an object comes closer to you, it becomes bigger. So those cues are there. I mean, we could imagine doing this task with stereo and so on.
Mhm.
All that is to be done.
Thank you.
Maybe can, yeah, so very simple question, but really very interesting. So what about uncertainty? So it's good to have a representation that you can use to manipulate things and have some kind of reinforcement learning agent that learns not through to those, but what about uncertainty? Should we take care in the representation side or just let the reinforcement agent?
Certainly at the representation side, because the action should be plan taking, knowing the uncertainty from perception. And I have papers on that too, but it's called uncertainty quantification. And I have a student called Anastasios Angelopoulos, and he has written many papers on this in the last year or two.
Okay, great, thanks.
Yeah.
Okay, thank you, and sorry for all the technical issues.